Dear students, today we'll discuss hydrogen bond, part of chemical bond, and important and special bond which has great application in biochemistry and organic chemistry. It is a special bond. Hydrogen atom, you know the first element in the periodic table. It has one orbital only, one s, smallest spherically symmetrical orbital, and it has a special quality. Parallelly, it can form two different bonds that you got in Bora. There are three sector, two electron bond. There you got one s orbital of hydrogen parallelly or two different bond with 2p of boron. That means this 1s has a special quality. A single orbital can form two bonds. Hydrogen bond like that bridge bond, but it is not bridge bond. It is a special bond, not like sigma or pi. Its energy not high like sigma or pi, but its energy much more greater than dipole-dipole attraction. See, in which condition an hydrogen atom will form hydrogen bond, that you have to know first. When hydrogen atom attached to it small size electronegative atom. Remember, small size electronegative atom. Later I will discuss why the size is small. Small size electronegative atom such as nitrogen, oxygen or fluorine. That means here X is nitrogen, oxygen or fluorine. The first condition is hydrogen must be attached or bonded with this nitrogen, oxygen or fluorine. Other can make hydrogen bond like chlorine also form hydrogen bond, but that hydrogen bond is not much more effective with respect to energy. Now, this hydrogen bond, this hydrogen, which is due to difference of electronegativity, you know this is delta minus, this is delta plus. And you can say here the hydrogen is partially vacant 1s orbital. Hydrogen has partially vacant 1s. Now, this hydrogen can make a special bond. The condition, it is attached to nitrogen, oxygen and fluorine, bond with small size electronegative atom. Here also X equals to nitrogen, oxygen or fluorine of another molecule, or it may be with same molecule. If another molecule, then it is intermolecular hydrogen bond. And if it is in same molecule, then it is intramolecular hydrogen bond. Here I am taking example. Let X equal to fluorine, nitrogen or oxygen. I told you that is delta plus due to electronegativity difference. This is delta minus. This is delta minus. This is delta plus due to electronegativity difference. This special bond is a hydrogen bond. But what is the difference? Says it is dipole-dipole attraction. Remember, dipole-dipole attraction, its corresponding energy near about 1 to 2 kilojoule per mole. Whereas you know, when X equals to nitrogen, oxygen or fluorine, then hydrogen bond energy near about 15 to 40 kilojoule per mole. Remember this. It's much more greater than dipole-dipole attraction. Now the question will arise, how this additional energy will come? How this energy greater than dipole-dipole attraction? Remember, this dipole-dipole attraction is the driving force to form the hydrogen bond. This dipole-dipole attraction will bring the X with close to H, but after when they are closely distant, then lone pair of small electronegative atom. You know, nitrogen normally trivalent, it has one lone pair. Oxygen normally bivalent, it has two lone pair. Fluorine normally monovalent, it has three lone pair. After this lone pair of small electronegative atom will overlap with the partially vacant of 1s, partially vacant of 1s. That means here partial covalency will get. Covalency. Covalency means overlap with the 2p of electronegative atom, or maybe it may be hybridized orbital with partially vacant of 1s. This sigma nature of the bond, this overlap mixing of atomic orbital or hybrid orbital being energy too much high, 15 to 40 kilojoule per mole. That is the origin of energy. And one thing remember, since here overlap will occur, overlap between this with this, and you know, when orbital will overlap along a particular direction, if like a sigma, like it is a directional bond like a sigma. You know, dipole-dipole interaction is not direction. Dipole-dipole interaction is not directional interaction. But hydrogen bond, remember, is a directional bond. Along any direction, hydrogen bond may var for. Hydrogen bond for along a particular direction, since there occurs overlap, partial covalency, and due to that partial covalency, energy is too much high, 15 to 40. And if we do consider this hydrogen bond, then correctly we will able to explain different properties of the molecule. Now, here I had shown here hydrogen bond that is intermolecular. It is intermolecular between two different molecules. Between two different molecules. Intermolecular hydrogen bond. Now, I told you, if this hydrogen will met hydrogen bond in the same molecule, then it is called intramolecular hydrogen bond. See the example of intramolecular hydrogen bond. I am taking an organic molecule, orthonitrophenol. See the structure of orthonitrophenol. You know orthonitrophenol. This is the structure. Phenol means weight. See, here this hydrogen will make hydrogen bond with oxygen load pair. And this hydrogen bond in the same molecule, that is intramolecular hydrogen bond. This is intramolecular hydrogen bond. Now, you got idea about the hydrogen bond? Now, the previously I told you the small electronegative atom. Now, question I think you got, why the small? You know, overlap integra depends on size of the atom. Where it is a very small, then overlap integral maximum more, and the corresponding energy released more. That's why small electronegative atom, the term is important. If I take phosphorus or sulfur or chlorine, size increases, and due to increase of size, overlap integral decreases, and you will not get effective hydrogen bond like high energy 50 to 40 kilojoule per mole. Remember this day. Now, I'll get some applications of hydrogen bond, which is magically explain some properties of the molecule. Most strongest hydrogen bond you will get in a salt that is called KHF2. KHF2 salt, you know, it will exist, but KHCF2, this salt not exist. And similarly, KHBr2 not exist, KHI2 not exist. The question will arise, this salt why exist and why they are not exist? Remember, this salt dissociates to K plus and HF2 minus. Remember, if it will exist, then this salt will exist. Now, go to the structure of this. The structure F minus and HF, there we get HF2 minus, and there we get hydrogen bond between F minus with this hydrogen. Condition is fulfilled. Hydrogen attached with electronegative atom fluorine, and due to this hydrogen bond, HF2 minus radical exists. That's why KHF2 exists. But what thing I want to mention here, the energy of this hydrogen bond abnormally 50 kilocalorie per mole. Surprisingly, 50 kilocalorie per mole means 210 kilojoule per mole. That means it is above 40. How hydrogen bond give huge amount of energy? Remember this. It is not purely hydrogen bond that I am going to explain. See, I'll take another canonical for break this bond. Made it F minus. And for here sigma, you will get another canonical form of HF2 minus. That is A phase, this is F minus. That means if these two canonical form are equivalent with similar energy and actual structure is the average of these two. If it is average of these two, that means this bond is not 100% hydrogen bond. This is 50% hydrogen, 50% sigma. This is also 50% sigma, 50% hydrogen. Due to inclusion of sigma characteristics, its energy 50 kilocalorie per mole or 210 kilojoule per mole. Remember, some type questions will come or already care maximum energy associated hydrogen bond that you will get in HF2 minus. Now, the orientation to form intramolecular hydrogen bond is important. I am to give an example where you will get idea orientation how important. I'll take an organic compound. Very simple. This is benzonitride. See here, benzonitride and orthohydroxybenzonitride. Apparently, you can take there may occur intramolecular hydrogen bond. 99% students answer should there occurs intramolecular hydrogen bond. But remember, if I draw the click structure of orthohydroxybenzonitride, the structure is C triple bond A and it is linear is p hybridized. The lone pair oriented along this direction and orientation never support to form the intramolecular hydrogen bond. Since lone pair oriented along above and hydrogen here, how they overlap? Overlap is not effective. Overlap will not occur effectively. Covalency, any covalency, that may be sigma or pi. Proper orientation is the essential criteria to form a bond. That's why here no intramolecular hydrogen bond. Remember, no intramolecular hydrogen bond. Remember this. See what idea about intermolecular hydrogen bond, intramolecular hydrogen bond. Now I'll go to give some examples how you will get the great application of hydrogen bond. Now first you have to know what parameters or what properties will change intermolecular hydrogen. Intermolecular application of intermolecular hydrogen bond. Molecular hydrogen bond. What application? Why twice I'm going to discuss. Intermolecular hydrogen bond, what it will do? It will increases the intermolecular relation. I told you hydrogen bond is a space of bond. Its corresponding energy much more greater than dipole-dipole attraction. It will increases the intermolecular attraction. That means the associated property of the molecule will be changed abnormally due to hydrogen bond. The associated property, tell me one example of associated property. Point. The first intermolecular hydrogen bond increases intermolecular attraction, increases boiling point abnormally. Next thing, if intermolecular attraction increases, then its volatility decreases. Remember, if volatility decreases, then its vapor pressure decreases. Remember, another property of liquid, if it is liquid, viscosity. Viscosity depends on intermolecular attraction. If hydrogen bond increases abnormal intermolecular attraction, it will increases the viscosity of the liquid. And surface tension. Surface tension also due to intermolecular attraction. Hydrogen bond increases intermolecular attraction, increases the surface tension of the liquid. Another thing, if solute will make hydrogen bond with the solvent, that is adhesive force. If there are hydrogen bond, for example, if any fluoride salt, any oxide, any fluoride salt, if you put in water, if you take in solvent water, they are formed hydrogen bond between solute and solvent. Like ammonium ion you have taken in water, they are formed hydrogen bond between solute ammonium park with water, and that will increases the solute solvent interaction, and which will increases the solubility of the solute in that solvent at a particular temperature. That means so many parameters, so many properties, all are associated property that we abnormally different if there are hydrogen bond. And intramolecular hydrogen bond, intramolecular hydrogen bond occurs in a molecule. That means, you will get an additional hydrogen bond in the molecule, and that additional hydrogen bond will decreases the energy of the molecule, will increases the stability of the molecule. That means intramolecular hydrogen bond reflect individual molecular property. One thing remember, if there are option of intermolecular hydrogen bond, if my right hand able to make hydrogen bond with left hand, then never my hand will make bond with other. Remember, always if there are option of intramolecular hydrogen bond, that part never participate in intermolecular hydrogen bond. If they are intramolecular, they are isolated, boiling point less, volatile more. If there are inter, boiling point more, volatility less. That I will apply in my different example. Before going to give the example, I have to share with you a part. Like the ammonium ion in water. Ammonium chloride or ammonium sulfate. Ammonia in water. Water here solvent, ammonium ion. You have put it ammonium ion. Now, can you tell me what different types of hydrogen bond formed here between ammonium ion and water molecule? Can you tell me? Apparently, you can take, sir, nitrogen of ammonium with hydrogen of water, oxygen of water with hydrogen of ammonia. These possibilities? Hydrogen of ammonium with oxygen of water, hydrogen of water with nitrogen of ammonia. But remember, in ammonium ion, I told you, I have discussed with you, it is plus charge. It has no lone pair of electron. And lone pair is the criteria to form the hydrogen bond. Since in ammonia or nitrogen, no lone pair. That's why this hydrogen bond, that is hydrogen of water and nitrogen of ammonia, never form since it has no lone pair. Lone pair is the criteria. Remember, it is a sigma-like overlap. And what type of hydrogen bond we form? Hydrogen bond. Here we get actually adhesive hydrogen bond for a molecule, that is the hydrogen of ammonia ion with oxygen of water. There are two lone pair on oxygen in water. Only this adhesive hydrogen bond you will get. And intermolecular hydrogen bond between the water molecule you will get normally. But between ammonium and water, only this hydrogen bond you will get. This will not get since no lone pair or nitrogen in ammonia. Remember this. Keep in your mind and remember in your mind that lone pair on small electronegative atom is the criteria to form the hydrogen bond. Now, one thing more I am going to discuss, which is the fundamental part of hydrogen bonding. That is, nitrogen normeric trivalent. There you will get one lone pair, and that lone pair available to for sigma. And sigma there, if I take it is 100% participation in overlap. hydrogen bond is 20% participation in overlap. We have nitrogen, one hydrogen bond for since one lone pair. And you know water, not only water, oxygen normally bivalent, and there you get two lone pair of electron. But remember, among these two lone pair, only one lone pair available to form sigma. H2O, you will get H3O plus. Never you will get H4O2 plus. Since the last lone pair is not available to form sigma. Since when it is O plus, it becomes highly electronegative. That electron pair tightly bounded by nucleus of O plus not available to form the hydrogen bond. But remember, both lone pair available to form hydrogen bond that you will get in water as well as in ice. The two number of hydrogen bond can form oxygen, any bivalent oxygen. Chlorine, you know, generally monovalent, and there you get three lone pair on fluorine. Remember, all three lone pair are not available to form hydrogen bond. And remember, no lone pair on fluorine available to form sigma. Never you will get H2A plus. Since it is highly electronegative, the electron pairs are tightly bounded by nucleus. Although no lone pair available to form sigma, but remember, one lone pair available to form hydrogen bond. Although it has three lone pair, but fluorine monovalent can only form one number of hydrogen bond. So, my dear students, you got the fundamental idea of hydrogen bond. What is hydrogen bond? Why we are specially discussing this part in chemical bonding, and its application is too much broad in organic molecule and biomolecules. In the next part of hydrogen bond, we'll discuss the application, specific application of hydrogen bond, which will abnormally change the property of the molecule. So, stay with us. Thank you to all.